All right, welcome. Today, we are diving into something that's, well, absolutely essential for anyone working with data: assessing for normality. I know, it sounds a little intimidating, but trust me, understanding this is a total game changer.
So, have you ever stopped to wonder if your data is actually playing by the rules? It's a really important question to ask because if it's not following one very specific rule, the conclusions you draw from your analysis could be, well, completely off base. So, what's this big, important rule all about?
Well, it's called the normality assumption. And look, this isn't just some dusty old theory from a textbook. Think of it more like a bouncer at a club. It decides whether or not you get to use some of the coolest, most powerful tools in your statistics toolbox. So here's the bottom line. Before you jump in and run something super common like a t-test, you have to check if your data comes from what we call a normally distributed population. If you skip this step, oh boy, you could end up thinking two groups are different when they're actually the same, or you could totally miss an important discovery. Basically, your entire analysis could be built on shaky ground, and that's why this one little check is such a huge deal. Okay, so how do we actually do this check? Well, the good news is we have a fantastic visual tool that's built for exactly this job. It's called the normal probability plot.
So, what on earth is that? Simply put, a normal probability plot is just a special kind of graph. It takes the data you actually have and puts it head to head with the data you would expect to see if everything was perfectly normal, like straight out of a statistics textbook.
And the logic behind it is actually pretty clever and not too complicated. On one axis, you've got your real-world data points. On the other axis, you've got these things called theoretical z-scores, which is just a technical way of saying, here's where those points should land in a perfect, normally distributed world. The whole idea is to see how well your reality matches up with that perfect ideal. The closer the match, the more normal your data is.
And this brings us to the first and honestly the most intuitive way to check for normality. Just looking at it. It's the visual check. You can often spot if something's up just by giving the plot a quick glance.
Okay, so what are you looking for? What's the good sign? If your data is normal or close to it, all those little dots on the plot are going to form a pretty straight line. I mean, a few little wiggles here and there are totally fine, but the big picture, the overall pattern, should look like a line. This is your green light. This is what you want to see.
But what if you don't see that? If you see a clear, obvious curve, where the points are all bending away from that imaginary straight line together, that, my friends, is a major red flag. A pattern like that is basically screaming at you that your data is not normal. It's probably skewed in one direction or the other.
But let's be honest. Our eyes can sometimes play tricks on us, right? So for a more rock-solid, definitive answer, we need to go beyond just eyeballing it. We need a simple mathematical confirmation, and that's where the correlation check comes in. And the process for this is wonderfully straightforward. It's just 3 steps. First, you calculate a number called the linear correlation coefficient. We just call it R for short. And it's basically a score for how straight your line of dots is. Second, you look up a benchmark number, which we call the critical value, from a special table. And finally, you just compare your number to the benchmark number. That's it. Now, this critical value isn't just some random number pulled out of thin air. It actually changes depending on your sample size, or N. Take a look here. See how a small sample size, say 5, has a lower bar to clear? But as your sample size gets bigger, like 30, that critical value gets higher. The test gets stricter. It expects the data to stick much closer to that perfect straight line. And this brings us to the one rule you really need to remember. It all boils down to one simple question. Is your R value, the one you calculated from your data, greater than the critical value you looked up in the table? If the answer is yes, then congratulations, your data passes the test. Okay, theory is one thing, but let's see how this works in the real world. Let's make this concrete. We're going to walk through a quick example together from beginning to end, and we'll use both the visual check and the correlation check. All right, here's our sample data. It's a small set, just 8 numbers, so our sample size, n, is 8. The mission, should we choose to accept it, is to figure out if these numbers could have come from a normal distribution. So, step 1, we plug these numbers into some software or a stats calculator, and out pops our correlation coefficient, R. And for this data, our R is 0.9970. Wow. I mean, a perfect straight line would have an R of 1, so this is incredibly close. That's a really, really good sign. Okay, on to step 2. We grab our table of critical values, we find the row for our sample size, which is n equals 8,
and we look up the benchmark number. And for a sample of 8, the critical value is 0.906.
And now we've reached the moment of truth, the final showdown. The question is simple. Is our number 0.9970 bigger than the table's number, 0.906? And the answer is a definite, resounding yes. Our calculated R of 0.9970 is way bigger than the critical value of 0.906. It doesn't just pass the test, it aces it. So, what does this mean? Because our R value sailed past that critical value, we can be really confident in our conclusion. It is totally reasonable to assume this data came from a normally distributed population, which means we're clear to proceed with our t-tests or whatever other analysis we had planned. Green light. So let's just wrap this all up into a neat little toolkit for you. You've got 2 main checks. First, the visual check. Just look at the plot. Do the points basically form a straight line? And second, the correlation check. Run the numbers. Is your calculated R bigger than the critical value from the table? If you can say yes to these, especially that second one, you are in fantastic shape. And there you have it. You are no longer just running statistical tests blindly. You are now fully equipped to check one of the most important assumptions that makes those tests valid in the first place. So the only question left is, what stories is your data waiting to tell you now that you know how to listen to it correctly?